Hello, welcome to the second day of 8.1. We're going to continue where we left off yesterday. If Corrine makes 75% of her free throws, assume that the free throws are independent, and find the probability she makes exactly 3 out of the 12 shots. Well, from yesterday, we do 12 choose 3, because that's how many different ways we can rearrange making 3 out of the 12 shots. That's 0.75 of a success. The probability of failure is 0.25. Now, if she makes 3, that's 0.75 to the third. That means that she's going to miss 9. All right, if we figure this out, it should be a very small, probably 0.00035. So it's very, very improbable that she'll only make 3 out of the 12 shots if her probability of making a free throw is actually 75%. Now, if we want to fill out all these, let's go back. And a way we could do this with our calculator is we could hit second vars, which brings up the distribution, which we do Binomial Cdf, and we do 12, because there's 12 shots. Probability of success is 0.75, and comma 3, because we want to find the probability that she gets 3 shots, and we should get the same answer. Alright, so if we want to fill in this entire distribution, take a second, pause the video, and fill this in on your own. Alright, hopefully you're back and you've done this. I'm going to fill in zeros down here because they're essentially 0. And then at 5, it starts up at 0.01, 6 is 0.04, 7 moves up to 0.10. So now we're at 10%, 26%, 23%, 13%, 3%. Oh, that was one off. Which one did I miss? Got 10, 19. So it should look like this. I apologize. 4%, 10, and then 19%, then 26 matches up. Okay, now it looks right. So this is our probability distribution for Corine's free throws. Now this is PDF because it's a probability distribution function. We find the probability of getting exactly 3. Now remember, with normal probabilities, we couldn't get exactly 3. So we'd never use the normal PDF. Now what if we want to find the probability if she makes greater than 7 shots? So let's go back here. Greater than 7, say greater than or equal to or greater than? Greater than 7 shots. Okay. So that means it would be 8 or more. So we just take those, add them up. So 0.19 plus 0.26 plus 0.23 plus 0.13 plus 0.03. There's about a 0.84 chance that she makes more than 7 shots out of those 12. So probability that she makes more than 7 shots is 0.84. Now there's another way we can do this with the cumulative distribution function. And what the cumulative distribution function does is it calculates the sum of the probabilities 0, 1, 2 on up to the value of x that we determine. So in this previous case, I could have done a binomial Cdf. Now that's in the same, just one spot below the binomial PDF. If I do 12, comma 0.75, comma 7, that will give me 7 and below. And so what I got for an answer here is 0.16. So if I take 1 minus 0.16, that'll give me everything above 7, which is 0.84. It's the same number we got up there. So if I want to do the binomial CDF for this problem, take a second and fill in all these data points. I'll start with, again, essentially 0, 0, 0, 0, 0.1, 0.5, 0.16, 0.35, 0.61, 0.84, 0.97, and 1. Notice how it ends with 1 because it adds up all of these probabilities. So when it gets to the last term, it should always equal 1. Alright, now we need to find the mean and standard deviation. The mean is n times p, which makes sense. We did that on a previous lesson. But the standard deviation is a little less intuitive. We take the square root of n times p times 1 minus p, or the n times the probability of success times the probability of failure, and square root. Now, if we want to find the mean and standard deviation for Creased free throws, the mean is going to be 12 times 0.75, which is 9. Standard deviation is going to be the square root of 12 times 0.75 times 1 minus 0.75, which is 0.25. So 12 times 0.75 times 0.25 is going to be 2.25. All right. Now, there's a study about attitudes for shopping. A sample of 2,500 adults were asked if they agree or disagree with the statement. I like buying new clothes, but shopping is often frustrating and time-consuming. Assume or suppose that 60% of adults actually agree with this. What is the probability that 1,520 or more of the sample will agree? Let's solve this in two ways. So we want to find the probability that x is greater than or just greater than or equal to 1,520. Now, if we did this with a CDF, what we'd want to do is 1 minus the CDF. So that's the probability x is less than 1520. So to find the probability that's less than 1520, we do a binomial CDF. We're going to start at with 2,500 people. The probability of success is 0.75, and we're going to go all the way up to 1519. All right, so binomial CDF, 2,500, comma 0.75, comma 1519. I got 0.157, or 0.158, so that's 1 minus 0.158, which is 0.84. So there's about an 84% chance that it will be 1,500 or more. Now, if we try to use a normal approximation, so let's look at our mean and standard deviation. To do the mean, we take 2,500 times 0.75, which is 1,875. We take square root of 2,500 as 0.75 times 0.25. And then we square root that number to get 21.65. So if I wanted to find the probability that it's going to be greater than or equal to 1520, that's going to equal 15 probability that my z-score is greater than or equal to 1520 minus my mean. Oh, I knew my mean was wrong. I just typed in the wrong number into my calculator. And I typed the wrong number here. For some reason, I'm thinking it's 0.75 when it's 0.6. I apologize. Let's go back through this. So this would be 1500, and this would be times 0.6 times 0.4. All right, take 2. 2,500 times 0.6 times 0.4. Square root that. This becomes 24.5. So now we're doing the z is greater than 1,520 minus 1,500 over 24.5. So this is probability my z is greater than or equal to 0.8163. And that's, if I do a normal CDF, 0.8163 to a very, very big number, I should get about 0.21. Now that is not what I got here, because idiotically, I did 0.75. I'm still thinking of the previous problem. Now let's do this for 0.6. This is the worst lesson ever with me making mistakes. So hopefully you're able to understand despite my many mistakes. So this now is 0.7869, and this is 0.213. And over here we got 0.207. So you can see the normal approximation was 0.207, where the binomial was 0.213. So this is approximately normal. If you look at the graph, if I draw a normal curve with the binomial distribution, you can see that it's a little off. It's not perfectly normal, but it's a normal approximation. So our answer isn't going to be exactly right, but it's going to be close. So we can use normal approximations when NP is greater than 10 and n times 1 minus p is greater than 10. So in our previous situation, we could use it because 2,500 times 0.6, 2,500 times 0.6 is equal to 1,500, which is greater than 10 easily. And then 2,500 times 0.4 is 1,000, which is greater than 10. So that works. So since these numbers are so big, it's going to be pretty close to a normal graph. If these numbers are really close to 10, it makes the normal approximation less good. But we'll say if NP is greater than 10 and n times 1 minus p is greater than 10, that's good enough to use a normal approximation. All right, if a football kicker makes a 30-yard field goal 80% of the time, assume that each kick is independent, can we use a normal approximation to find the probability of kicking 18 field goals out of 20 tries? Well, let's do 20 times 0.8. That's 16. That's greater than 10. So that works. 20 times the chance of failure, 0.2 is 4. And that is not greater than 10. So we cannot use a normal approximation. How many kicks would be the minimum in order to for it to be approximately normal? We'll have to check two equations. NP is greater than 10, and n times 1 minus p is greater than 10. So our probability in this previous situation was 80%. So n times 0.8 is greater than 10, then n times 0.2 is greater than 10. So if I take both sides and divide to figure out what this would be, 10 divided by 0.8 is 12.5. 10 divided by 0.2 is 50. So n, we take the larger of the two. So n has to be greater than 50 in order to use a normal approximation. All right, that's our lesson. Here's the homework, and good luck.